Hello, everybody. I'm Arben Galzici, the Instructional Materials Manager at Wolfram U, and I'd like to welcome you to the final session in our new in 14.3 webinar series. Over the past 3 weeks, we've covered a lot of ground related to updated and new functionality in version 14.3 of Mathematica and Wolfram Language. And if you missed the previous sessions in this series, I just wanted to let you know that you can access the recordings right here on the webinar series landing page if you just go through here. I think you might have to back up to the full webinar series landing page instead of the particular one for today, but you'll find them on this page. Version 14.3, as you've no doubt realized by now, is a big release with quite a few new important features, and there's a lot of improvements to core functionality as well. On that front, I do invite you, in addition to attending these sessions, to check out Stephen Wolfram's blog post here, where he covers a lot of the new functionality in quite some detail. I think it's nice to have kind of a written version here as well as the video presentations. Today, we're pleased to welcome the developers responsible for geometric modeling and computing in Wolfram Language and some new features in Wolfram Compiler. We've got Tom Wickham-Jones, the Director of Kernel Technology here at Wolfram Research, as well as Charles Pu, Jae-Woong Jung, Alex Schettelbauer of our Discrete Computation Group. If you'd like to try the examples from today's webinar, you will, of course, want to have access to version 14.3, and we'll share a free trial offer right here so that you can get started with that right away. I'm going to ask a quick poll question just to see about how much of the audience has already upgraded to version 14.3. And we do also have a YouTube live stream audience. So for those of you on YouTube, please feel free to type your responses as well as your comments and questions in the chat over there on YouTube. We're over here on Big Marker, so if you're on YouTube, feel free to put your stuff in the chat there. We do have Wolfram Webinar and technical staff joining behind the scenes to help us coordinate the Q&A between both the webinar here on Big Marker and the live stream on YouTube. So feel free to put those questions in the chat as we go along, and our staff will do our best to answer what we can in typed responses to you. And if you don't see a quick response to your question, please be patient. We will save some questions for the team to address at the end of their presentations. And we'll just try and do our best to pick questions that fit that idea. Let's see the poll question here. I'll give this a little bit more time. It's always a little bit slow to load the results from people here on Big Marker. And as more people finish up submitting their responses there, I'd just like to remind you that there is a download link for the presentation notebooks from all the sessions in this series in the sticky note in the webinar interface at the top of the chat and Q&A pane. It's in kind of a tealish or seafoam green maybe, and it says download today's handout. And if you click on that, you'll be able to get all of the notebooks that we've used in these sessions, and you'll be able to open them up and play with them yourself. Okay, thank you for your responses to that poll. It looks like a very large majority, over 90% of people have already upgraded to version 14.3, and that's great to see. So everybody who's already upgraded, you'll be able to interact with all the functionality in those notebooks. And I think I will, without any further delay, hand things over to Tom to get us started.
Right, so let me just get started. Right, so I think I'm all set to get started. So I'm Tom Wickham-Jones. I've worked on all sorts of parts of the Wolfram ecosystem, technology, Mathematica for many years. And over the past years, I've been working on the Wolfram compiler. So today, this is, as has been explained, this is a sequence of things new in Wolfram 14.3, and I'm going to be talking about the Wolfram compiler. So I'm just going to start by talking a little bit about what the compiler is and give some, introductory material to it just to help people get started rather than looking at all the new features. So the compiler is a long-term project that's been running for a few years, and the idea is it can to convert Wolfram language code into native machine instructions. So it provides, can provide dramatic speed enhancements for Wolfram language programs, and itself is a high performance language with unique and innovative features, and it provides like new and interesting opportunities for things like linking to external libraries and accessing new technologies. An increasing amount of Wolfram language features are built with it, and it's the basis of the Wolfram data structure library. So in this presentation, I'm going to give a brief introduction to the compiler and describe some of the new 14.3 features. So getting started with the compiler. So there's different ways, but one way is to start with a Wolfram function. So this is a function with an argument and a body. But we add a type annotation to the argument, and then we can compile this, and we get this compiled code function, which can be fed arguments and return a result. So as you see, we're testing if it's all true, that everything's greater than 0, and that's true. Now, you can also use the uncompiled code, and they both get the same answer, but they're using different routes. The compiled code has quite a significant speed advantage, so we can see that just by using the repeated timing function, and we can see here that we've got lots of zeros there and not so many zeros there. So this is quite good acceleration that we're getting for this function. The compiler has a very sophisticated state-of-the-art type system where you can add like different functions that you might call. Here's a function declaration, and I'm giving it a name. So in this type declaration, I'm giving it a type, but I've not said I'm saying it's a packed array, but I haven't said what the packed array contains. So then I can feed that declaration in and make a call to it. So I'm calling it here with machine integers, or I can call it with double precision numbers. And so the same code, I didn't have to change this. Same code works in different ways. And that's a big part of how the compiler works. So this little bit of code can go a long way. We also can integrate with other Wolfram language, ways of working. So I can write code with like regular pattern definitions. So this is more typical way of writing. I make a declaration. So I'm giving it a type signature, and I'm saying down values function. That means use these values. And then I can compile this and run it. And so the point there is there's different routes to reach compiled code, and they support different types of workflow. But the one that I quite like is to sort of start prototyping with interpreted code and then transitioning to compiled things, and writing these like pattern definitions is quite a good way to get there. Another feature that's been built, this has been existing for many years, is the Wolfram data structure library, a library of data structures built with the compiler. And one of the things about these is they are automatically available. You don't need to run the compiler. We've done all the work. And you can see here a list of the data structures that we have available. We add to these and we improve these with every version. And if there are things you think are missing, let us know and we can see about adding them. And here's just a little bit of an idea. These also can have different semantics. And so this is like an extensible array, but it's mutable. And this allows us to have very fast append operations. So I'm appending 10,000 elements. If I did this with a traditional list structure, it's considerably slower because the traditional expression is not mutable, so it needs to make copies in that way. So that's, if you can switch your code to using these data structures often, that's quite a beneficial way to work. Right, let's actually get started with 14.3. So we'll talk about some of the new features in 14.3. And I just summarize these in these areas. We have new documentation. We have some ergonomic improvements. We have improved Wolfram Language integration and support improvements. And we have these incremental functions. So let's come and have a look at these. So the first thing I want to draw your attention to is the new documentation. The compiler is powerful, but it can be hard to use. And we've now included this large tutorial on using the compiler, which is included both in product and online. So here I'm just going to open the, this is like the online thing. And, you know, there's quite a lot of stuff here with different examples and working with, you know, data structures, you know, all sorts of different useful examples and explanations and such like. So that's kind of, you know, all kind of useful. One of the, actually a side effect of writing this documentation is that we have quite nice LLM functionality through Notebook Assistant, and Notebook Assistant is able to make use of this documentation and stuff. So it can provide from sort of natural language queries, it can make use of that. But, you know, the traditional way of reading material and seeing examples is very accessible there. To find the tutorial, we've added links from many, you know, compiler-related pages. So this is the documentation page for function compile, and in the text notes section, we see there's links, and that's true for all of the compiler-related, you know, documentation. You can reach this tutorial, which is pretty useful. I've been giving presentations on the compiler for a few years, and every time people ask, oh, is there a tutorial? And we've had internal versions of this that people have wanted me to share, but it's much better to get this out sort of officially. Right, next feature is looking at some of the ergonomics or tools that we provide to work with the compiler. So this compiler information is something that's been around for quite a few versions. So I can look up information on types and functions. So here, for example, this is the integer 64 type, and you can see some of the sort of type hierarchy that fits into this. The meaning of these sorts of things is, of course, explained in the documentation. And here I'm going to look at a function definition. So when you look up a you know, to raw pointer in a function, you get some links to documentation, and there's various, you can see the implementations of things. Now, sometimes with the way the compiler is written, you get you get a lot of these things coming up. And so this is new in 14.3, is to allow you to select a particular function based upon its type. So for example, if I just want to see versions of to raw pointer that return a C array, I can use pattern matching language using the regular pattern matcher to see, you know, just those, narrow down the search and see things and help to use it. And searching for compiler related stuff is obviously very important. Another new feature that we've added is this is going to become the basis for a better error handling system, but it's useful even now. And this is a way to get inside compiled code to figure out what the name of the function is or what its type signature is and things. And so what I'm doing is I'm got some code and I've just stuck in like an echo into that. So when I execute it, it echoes the compiled function data. It shows the type for the function that we see. You know, it takes an integer and it's returning a packed array. This function doesn't have a name, but if it had a name, you would see the name there. So that's kind of useful for, you know, tracking down errors and things. Right, another feature that we've had for a while is down values function. And, again, here's a little reminder. I can make a pattern down values definition, and then I can reach it from compiled code. And in the new version, we've extended this and improved it, and we have support for more pattern constructs like except, alternatives, and certain pattern sequences that you see like here. So these are the patterns, and I can call code, compiled code, to access them. And the basic direction that this is going in is to have the compiler to support pattern matching in things like cases or delete cases or whatever. And the way that it works on this is kind of interesting, because it actually generates a function that embodies the matching of the pattern, and then it compiles that. So it's actually quite optimized. That's kind of interesting. Another area of advance in the new version is the in various functions that we try to work on. So we have this bit vector data structure, which is used very extensively in, for example, in the tabular, the new data handling functionality. So a bit vector is kind of like a super efficient compressed array of bits, but it's like super efficient because it uses these bit operations, and it has like these parallel ways of working. So that's kind of interesting. And then we've improved some of the other operations that we see there. Right, now let's come and look at these incremental functions. To me, these are like super interesting. So incremental functions are functions that can be paused and then resumed. So that's in contrast to a sort of traditional type of function where you call the function and it runs to execution and exits, but you can't like freeze it in the middle. You just get the result. Now, here we see, so we add this incremental function wrapper, and it starts executing the code that we see here. So it has two of these yield points. So we're going to compile this, and it returns an incremental function object. So we call the compile function, and this is returning a data structure that holds the running function. And we gave it an argument, 10. So we can wake up the function by calling next. So this is running to the first yield point and running 10 plus 1, which is 11. And then we can call it again. And this runs to the next one. It runs 10 plus 2, which is 12. But the function's now finished. And if we call next again, we get a failure object. It's finished. Now, very typically, you would use these incremental functions in a loop. And then they're like some type of iterator. So this is an example I have here that's basically looping forever, and it's generating Fibonacci numbers. So it starts with a seed, and then it's doing like a swap of the numbers, where it's sort of incrementing them. So that's kind of a concise way of, the compiler actually optimizes this sort of construction. So it doesn't actually create the lists, it just makes the assignments, sort of thing that a compiler can do. So we're going to instantiate this. It takes no arguments. And then every time we call next, we get another number from the Fibonacci sequence. So as I keep calling this, it's going to get bigger and bigger. So that's the incremental function generating a Fibonacci sequence. Now you can do, I'm not going to go through all of these examples because there probably isn't time, but this was an interesting one. This was a cipher, a Vernam cipher, and what it's doing is it's iterating. So there's kind of like a do loop here. It's iterating over the characters in a string. So this is each character, and then it's doing a bit XOR with a key that's a cipher that's passed in, and then you can do this, and that's kind of a fun example. the point about this is it returns each character one at a time. So if you wanted to put them into some other code and not wait for the end, you could do that. So incremental yield can also, I mean, you can put it anywhere in a function. So here I'm generating something a little bit like outer. So let's compile this. And so I've got a loop, and I'm basically iterating over the elements of two lists, and I'm yielding a list of the two things. And you can see, let's compile this, and this is returning. So I've set it up. It's waiting. Every time I call next, it's going to return another element. So this is similar to doing list, doing outer over the list. It's returning the same sequence. So just keeping a little eye on time, and hopefully this isn't too much detail. The documentation has these sorts of examples. I'm going to show something that starts to get, I think, really quite interesting. So now I'm going to make a function declaration, and it's got the same sort of thing. And this thing here is, I'm also passing in a function. So it's not just the list. It can be anything. Now I'm going to call that declaration here. And I'm passing in the function that's adding the elements. So I'm going to generate pairs of the two lists. And we can see how this works. Yeah, I'm just putting this into a table, and it's basically just generating the addition. But what's kind of cool about this is the same declaration can be used for something different. So here I'm using it for expressions. So we compile this, and here the function is just combining the things in a list, and it comes out, and here we go. So this is one definition is working in different places. And I've got an example here where it's working with a red-black tree. And here, the same definition is working itself with an incremental function. So here, I'm compiling this. So one of the sources is an incremental function, and the other is a packed array. So I'm going to use this Fibonacci incremental function, and we run like this. And so here I'm doing an outer product over an infinite sequence where one of the sources is infinite. So obviously I can't run this to the end. I'm sort of limited like that. But that's, I think, kind of interesting. And then maybe a last interesting example is where we have an incremental function that calls itself, like a recursive, and you can implement some quite interesting algorithms. So this one here is it's iterating over the elements. If it's an atom, it yields the thing. Otherwise, it's going to iterate over each element, calling itself on that. And this is basically doing a flatten operation. So we can see that here. And if I pass in a big list of things, I can iterate over extracting all the elements. Now, if you wanted all of the elements as a list, it's probably better just to use flatten. But this is still quite an interesting thing, and it has the benefit of generating them one at a time. So you might want to stop when you've reached some point. Okay, nearly finished. I'm going to just make the point, incremental function only works in compiled code. It needs the machinery of the compiler to be able to freeze and resume. But just remember that compiled code quite easily calls the evaluator. The new documentation has lots of examples and ways that this can be done. So this is really quite general. And I had an example here of using Wolfram Language file IO operations in an incremental function. I'm not going to work on that. And I think I'm coming to the end of my time, so I'm going to give a summary, and then I'll probably drop out, but there'll be a chat system where I can answer questions while the next presentations are going on if people have questions or and so on. Anyway, so I gave a very brief introduction to the compiler. Then I talked about new features in 14.3. These include the big thing, I think, is this extensive tutorial on the compiler with use cases and explanations and examples. I showed some of the improvements for compiler ergonomics, some of the integration of the compiler with the Wolfram language, such as the pattern matcher integration. And then finally, I was talking about incremental function, which is an entirely new programming paradigm, which we expect to be building out with more features around this in upcoming versions, but in itself is quite a useful thing. Anyway, thank you very much. So I'm going to stop sharing my screen, and then I'm going to go mute, but I'll be hanging around a bit, answering questions. Anyway, thanks very much, everybody. Okay, cheers then.
Thank you very much, Tom. I really appreciate that overview of the new functionality, and certainly am happy that we have that tutorial now publicly available for everybody. So I think we'll now move on to this presentation by Charles, Jabum, and Alec.
Hi, my name is Alex Schillebauer, and today I'm going to talk about the latest advancements in geometric modeling and computing in the Wolfram language. Let's start with a quick summary of today's talk. We'll begin with an overview of geometry to help give you an idea of our continued development of our geometry framework. Then we'll go into some exciting new developments in the areas of mesh processing and subdivision surfaces. Here is a timeline for geometry in the Wolfram language. Under each version, we'll see just a few of the features that were added with that version. Going all the way back to 2014, we'll see the introduction of the geometry framework with version 10. This added regions, which are shapes that we can compute on. This includes things like calculating their area, volume, bounds, and much more. This all laid a very solid foundation for geometry in the Wolfram language, one that we have continued to build upon with future versions. Going into version 11, we see the focus on 3D printing and the various operations that required, such as detecting and repairing mesh defects. Going to version 12, we see a deep focus on generalizing our polygons and polyhedra, such that we can extend our region computations to geodesic ones. This allows us to do things like calculate the distances between cities or the area of countries, all on the surface of the Earth. In version 13, we saw the introduction of a new way to represent regions through constructive solid geometry, or CSG for short. This allowed us to optimize the process of modeling with Boolean operations common in many CAD applications. And lastly, we have the current version of 14. This added functionality around mesh processing, subdivision regions, and even curvature and shortest paths. These will be the focus of today's talk. All this functionality comes together to form our geometry framework. You can think about it as a pipeline with different goals at each step along the way. Each new feature should then support one or more of these goals. So starting from the left, we have ingest. This is where we want to bring data into our system. It should be like a scan data, such as a point cloud. It could be an existing object in some 3D format, like STL, OBJ, USD, and much more. It could even be data we generate ourselves through some mathematical process. But once we have this data in our system, we want to be able to model it and choose the best representation to do so. For example, if we have a solid region, we might want to use a CSG to model it. If we have a nice smooth surface, we probably want to use the B-spline to model that. And as a fallback, we always have meshes, which are able to approximate any region up to some precision. Once we have our model, we want to compute on it to derive new data. This could be properties like its area or center of mass. It could mean applying a solver to it, such as integrating over its surface or volume. He may be processing it to create new models or refine the old one. And lastly, here we have synthesize. Once we have our model and we've done compute on it, we want to have a tangible output. This could be a visualization, such as a high-quality render. It could mean exporting our model to AR formats, so we could actually interact with it in a virtual environment. It can even be performing simulations to make informed decisions about some real-world system. But keep in mind that this diagram is not comprehensive, though I hope it gives you a good idea of our overall vision for geometry. That concludes our overview of geometry. Let's now move on to new features that are being added, such as curvatures and paths. Here we're going to go over some new functions for calculating different types of curvatures on regions. We're going to look at some surface plots that let you visualize these, among other things. And we're going to look at some shortest path calculation within a region. All right, first we have curvatures. So here we have 4 new functions for calculating 4 different types of curvature. We have the Gaussian, mean, min, and max curvatures. To demonstrate them, we can go ahead and create a special surface called a Gorsat surface. This gives us kind of a nice rounded cube here. And then go ahead and find a point on that surface and show it as a black dot here. And then we can find the curvature at that point for these 4 different types of curvature. The first here is the Gaussian, followed by the mean, then the min, and lastly, the max. Now you can note that these are all exact values and not approximations of the curvature. Now it can be hard to visualize how the curvature varies across the surface of a region. For this reason, and to help visualize any arbitrary function across the surface, we've added 2 new functions here, surface density plot 3D and surface contour plot 3D. To show how these work, I'll once again create our surface here. And then I'll go ahead and plot the Gaussian curvature across that surface using surface density plot 3D. This gives us a nice gradient from positive to negative values here of our Gaussian curvature. Now for a Gaussian curvature, the sign actually corresponds to the shape of the local surface. For example, a very positive value, like at these corners, corresponds to a kind of spherical shape. A value close to 0, like here, implies a flat shape. And a negative value, like at these edges, implies a saddle shape, where the curvature kind of goes against each other in 2 different directions, like a saddle or potato chip. Now we have our second function here, surface contour plot 3D. This is the same, except for instead of a smooth gradient of values, it'll create discrete contours, which can be handy if you're trying to visualize certain regions of curvature or some other function value. And just to show this is not just for curvature, here we have kind of arbitrary function x times y plus z that we can also plot on our surface. And there we go. All right, next is shortest path. Here we want to find the shortest path between 2 points in a region where that path stays within that region as well. So we have 2 new functions for this, find shortest curve and shortest curve distance. So I'll use the first one here to find the curve between 2 points within this annulus. We show that curve in red, and you can see how it bends upward to avoid this hole in the middle in order to stay within the region. I can then get the distance of that red curve. See, it's a little below 1.5 units. And I did the same in 3D by finding the curve between 2 points on the surface of a torus. So go ahead and do that and visualize it here. And we'll see our torus with this red curve showing the path between points on either side of it. And we notice that the curve still kind of skirts the hole in order to stay on the surface of the torus. And we can see once again that its distance here, this time it's a little above 2.5 units. Now these functions can be useful for things like pathfinding and constrained environments, where there might be areas that are off limits to you for whatever reason. Now we'll look at our first major area of new development, mesh processing. I'll cover what it is, 3 techniques we use for it, and their applications. So what is mesh processing? Well, oftentimes the meshes we encounter are not of good quality, or at least not for a task we want to use them for. For example, they can be too complex and have too many polygons. They could be noisy from poor scan data, or they could be irregular, where they have triangles of different shapes and sizes. All 3 of these can cause issues for certain tasks. And this is what mesh processing is meant to resolve. Mesh processing uses various techniques to try to optimize these meshes according to some criteria in order to fix these problems. Our first technique is mesh simplification. Here the goal is to reduce the polygon count while preserving the overall shape of the object. We can see an example below here, where we start on the far left with our very dense mesh. In the middle, we then have our more reasonably sized mesh. And on the far right, we have a very sparse mesh as almost low poly. But despite them all having different polygon counts, they all maintain the same rough shape. A common application of mesh simplification is levels of detail. Whenever you're trying to render something in real time, like in a video game, you want to reduce the amount of triangles you're rendering per frame. One way of doing this is with levels of detail, where the idea is we render our object with different meshes based on how close it is to the camera. When it's very close, we can use a high resolution mesh. When it's very far away, we can use a low resolution mesh and save on our triangle count. To generate these levels of detail, we can use mesh simplification. So as an example here, we can use our new function, simplify mesh, which does just that. So here we take our base mesh at full resolution, and we have 2 additional levels of detail that use less triangles. Now, while you can tell a difference when they're all viewed at the same size, if we view them from different distances, then it becomes much harder to tell the meshes apart. Despite this, the one on the far right uses far fewer triangles, which will save on render time. Our next technique is mesh smoothing. Here the idea is to try to remove noise from a mesh that could have been introduced from something like 3D scanning. By removing it, we can create a nice smooth surface which better represents the original object. One application of this is heritage preservation. We often want to 3D scan historic artifacts in order to better preserve them digitally and allow more people to experience them. For example, here, we can use our new function, smooth mesh, and apply it to this very noisy artifact scan. After doing so, we get a much smoother mesh that looks much more like the original model. Our final technique here is mesh refinement. Here the goal is to rebuild a surface made of triangles of various sizes and shapes into one made of uniformly sized triangles. This can be very helpful in areas such as finite element methods, as well as reducing certain rendering artifacts. So another application is making meshes more animation friendly. Oftentimes, if you have a mesh with a lot of skinny triangles, like we see in this cow, and you try to deform it or animate it, it kind of becomes very noticeable. It appears overly stiff where these triangles occur. So here we can use our new function here called remesh and apply it to our cow here to get a new mesh with much nicer triangles that are all very uniform across the entire cow surface. We can even have a little example animation here where we see the cow being deformed by kind of blowing it up like a balloon on the left here, which appears a little stiff. Then we can see for the new remesh cow on the right, and it kind of bends a little more naturally. Our second major area of data development is subdivision surfaces. Here I'll describe what they are, how to represent them, and their applications. So what is a subdivision surface? Well, subdivision is a process where we take a coarse base mesh and make a more refined, smoother version of it. This is different from the mesh smoothing we saw in mesh processing, as that was meant to remove small, noisy details from an already dense mesh. Meanwhile, subdivision surfaces do the opposite. They add more detail to a coarse mesh, use that as sort of template. So how do subdivision surfaces actually work? What we do is we take each polygon in the base mesh, and then we'll subdivide it into smaller polygons, usually 4, and then we'll take the vertices of those polygons and slightly adjust them. When we perform this on all the polygons of the mesh, the entire mesh becomes smoother and rounder with each iteration. We call these iterations levels, and we consider level 0 to be the original base mesh. As we increase the number of subdivision levels, our mesh becomes smoother and smoother. Eventually, as it approaches infinity, our surface will approach something called the limit surface. Unlike the previous finite levels, this limit surface is unique and that it is mathematically smooth and not made up of discrete polygons. Now let's look at how we represent subdivision surfaces in the Wolfram language. We do this using the new symbol subdivision region. In order to represent a finite subdivision level, we can pass the base region and the level to subdivision region. For example, doing it with this tetrahedron will give me the second subdivision level for this tetrahedron. We can also look at the various levels from 0 to 3 here, and we see how our tetrahedron gets more and more rounded off as we increase the level. We can also represent the limit surface by excluding that second argument. So here, if we just pass the tetrahedron, we see we now have the nice, perfectly smooth region that represents the limit surface of our base tetrahedron. Okay, now I'll cover a few applications of subdivision surfaces. The first here is also the most, which is modeling smooth surfaces. This is very common in the entertainment industry, such as in movies or in games or even animations. Whenever an artist needs to model a smooth surface, they'll usually turn towards subdivision. This is for a few reasons. The first is ease of modeling. An artist can easily model its low-poly meshes, like this hippo, by hand, and then leave the tedious work of smoothing it out to the subdivision process. Also, there's workflow compatibility, where often subdivision models are easier to texture and animate than the alternatives like NURBS. Similarly, when it comes to rendering, since subdivision can easily be turned to a mesh, which renders very quickly, it performs very well when rendering, compared to other alternatives like NURBS, which can be a little trickier and require special shaders. All right, and then as an example here, so we can see this very coarse base mesh of a hippo. If we want to make that smooth, we can just calculate the limit surface with subdivision region and get a nice smooth model here. You can imagine that modeling this low poly version would be much easier than this very high poly smooth version. In addition, if you ever needed to make a change, something that would take probably hundreds of updates on this final smooth version would take only 1 or 2 changes to vertices on this base version, which makes it much easier to edit or update your mesh as you're going along. Our second application is adaptive model fidelity. The idea here is we don't want to render our model with more polygons than we need to. This is useful in cases such as scene assembly, when you're arranging objects, lighting, and cameras to render a scene. Also for animation and rigging, when you're setting up a model to be animated and setting the keyframes of that animation. And lastly, for levels of detail, which as we mentioned before is common in stuff like video games, where you want to minimize the number of triangles you're rendering per frame to improve performance. However, where this differs from what we previously looked at with Simplify Mesh is that instead of removing detail, we are now adding it to a base mesh. So here I'll use a base mesh of a coarse teddy bear, and I'll add detail by applying subdivision a couple times. And now we have our 3 levels of detail here. Once again, they're very obvious when you see them all at the same size, but if we move the smaller ones further back, we can see that they all look roughly the same. However, we're saving a lot of triangles when rendering our object from far away. Our last application is interpolating smooth data. Sometimes you have sparsely sampled data from an underlying region you know to be smooth. In these cases, it can be helpful to use subdivision to sort of reconstruct that smooth region. One example of this is with claw simulations. In claw simulations, you want to reduce the number of sample points you use in order to minimize the amount of time it takes to compute your simulation. In this example here, I have simulated a cloth using a sparse number of sample points. And we go ahead and play that simulation. And we see how the cloth sort of wraps around the sphere here. However, this is not super convincing due to the sparse nature of the points. However, if we go ahead and add subdivision to this, as well as a nice shader, we get a much more convincing cloth. If I pause that here, we can even rotate around. This looks much nicer in comparison. Hi, my name is Alex Schillebauer, and today I'm going to talk about the latest advancements. Easier to this looks much nicer in comparison.
Sorry about that little technical hiccup there, folks. We've got a couple questions that I think we're waiting for answers on. Publish that. And certainly if Alec, Charles, or Jalen would like to mic up to answer some of these questions that have come in from YouTube, you can feel free to, but you can also answer over text. Let me see if any answers, if I can see any typing indicators. So there's a question from Anthony here, for example. Well, there's one getting answered by Charles right now, which is from Michael Salami on YouTube, which asks whether there's support for texture materials in import and export. So Charles is answering that one now.
I can probably give a live answer, actually, much easier than writing, if that's okay.
Yeah, of course.
Thank you. Yeah, so we are definitely working on adding support of texture material in import and export, right? And we added support of texture in OBJ, and we are still working on format like USD. It's a complex work, but we hope to, fully support texture, color, and other, visual property in our import and export files. So stay tuned, and we'll try to kind of keep you updated with that work. Thanks.
Okay, excellent. We will indeed stay tuned for textures. And we had a question from Anthony and a question from Bob. I'm not sure if folks have an answer to this one. I'm very ignorant about a lot of this geometry and mesh stuff. So I don't know what ARAP is, so I have no sense of this, but maybe our developers have an answer for that one. Going once, going twice.
Again, I'll give a live answer.
Yeah, please do.
At this stage, we haven't yet have, I believe ARAP is rigid deformations, I believe, or deformation of a mesh in that form. So that's a good suggestion. We'll keep that in mind and see how we can integrate it in future release. And there was an additional question from Wilford Smith. How about import and export of more card format? And yes, as you know, we added step and edges, and we hope to continue through that directions. And the future release, there will be a focus on card, especially on boundary spline and such. And we hope to actually, at that time, complete our work on import and export of card systems.
All right.
And that final question from Bob, I see. So can we put creases in our subdivision? By that, I think you mean a lot of times for subdivision, you can put creases on certain edges to prevent it from being smoothed too much. So right now, we do not support that. The entire mesh will be fully smoothed when you apply subdivision. But that is something we're looking into, being able to add creases to better control what parts of the mesh get smooth and which ones do not.
Okay, thank you. I think that answers all the questions we have. Here comes another one from Christopher French. I'll put that on screen. Missing a verb there, I think, but probably fine.
Yes, definitely. So the find shortest curve actually gives you the minimal curve, minimal length, essentially, from a starting point to a endpoint destinations.
Mhm. Okay, any more questions, folks? I don't think I see any on YouTube. Okay, if there are no more questions, I'd just like to thank everybody for attending today's webinar, and of course, give my thanks to Tom, Charles, Jayboom, and Alec, and also to our behind-the-scenes staff who have been keeping things running smoothly. Please do take just a minute to answer the short survey that'll appear in your browser as you exit. It's very short, and it includes a question about getting a certificate of attendance from this event. That's all for today. I hope we see you again soon. Have a lovely rest of your day.